and it's my pleasure to introduce Gareth from voxeljet, who's going to enlighten us about what's going on in the 3D side of things. Gareth studied mechanical engineering at Southampton, and he was actually from outside the casting industry, but now that's one of his specialisations. So over to you, Gareth.
So good afternoon, everyone. As Angela mentioned, I'm Gareth. I work for voxeljet. I've been with voxeljet for about a year and a half now. I have a background in engineering, and even though I'm very new to the company, new to the industry, don't be alarmed. The material in my presentation has been filtered down. My presentation material has been filtered down by my boss, James Reeves. But not only James, also one of the very pioneers of sand printing, Dr. Ingo in Germany. So all the material in here is very relevant, and hopefully you'll find it useful. So, my presentation, firstly I'd just like to introduce you to my company, voxeljet. I then want to take you through the Foundry applications, 3D printing, followed by an overview of metal printing and what we understand metal printing to be, and where that's going to head. And then finally the developments we expect to see in our technologies for the sand and investment casting industry. So, a little bit about us to start off with. We were founded in 1999, and we were listed on the New York Stock Exchange in 2013. So you can see we're not a gimmick, we're quite a big company. We've got over 300 employees now, with a headquarter in Germany, and subsidiaries in Milton Keynes, so a 15-minute drive from here, where we have both sand printing capabilities and capabilities for printing for the investment casting industry. We also have subsidiaries in India, China, and the US. So, a little bit about our business. We not only provide printing services, but we also manufacture the machines. So we think the two come hand in hand. No one's going to invest in a machine unless you have confidence in the printed parts that come out of it. So in Milton Keynes, we've put a big investment in place. We've got enough room for 3 sand printers and 3 printers to support the investment casting industry. We can supply UK foundries with these printed parts. You can test them in your processes, see if they work, and if they do, that's great. You know, if you get success from using our printed parts, perhaps you'd like to start buying more, and then eventually maybe look at a printer. One of these printers is a large investment. These are very big machines. Our mid-range model, for instance, has a print bed of 1 metre by 600 millimetres by 500 millimetres. Our largest printer has a print bed of 4 metres by 2 metre by 1 metre. So they're very big. We print in mainly 2 products. So we have the sand printing, and when I say sand, we can print in GS14, GS19 or GS25 sand, standard silica sand, or we can print in synthetic sands. So that's like Ceramide and Kerphalite. These sands have grains that are very spherical, so they give good casting properties for certain applications. The printed plastic for the investment casting industry burns out similar to a waxwood meltdown. So I'd just like to touch on the sand side of things briefly. So we have 3 main material sets. So the first one is the Furan, or the cold setting sand printing. This is the most established technology for us. We've got lots of capacity in our German service centre, and we're looking at getting some capacity in the UK. So, as it says on the slide, this sets under ambient temperature. Sometimes you might want to put fragile cores in the oven, just to take away some of the activator that might be left on the surface of the cores. We have plenty of capacity, as I mentioned. We actually provide a 5, 10 and 20 working day service. So you can get your mould and cores within just over a week. We've then got 2 other material sets here. These are the slightly more environmentally friendly ones. So in organics, which I understand the global community is trying to move towards, because it's 100% safe, friendly for the environment, there's no harmful emissions. But for us, at the moment, this hasn't come to a commercially viable machine. It will in the coming years. We then have phenolic. Again, this is a much better chemical process for the environment, and we do have machines for this process. Unlike the first material set that I mentioned, you do require heat to cure the binding agent. So, we try to centre everything we do around productivity. So, as I've mentioned, the machines are very, very big. So you can print big things, or you can print lots of small things. You don't have to just dedicate one printer to one part. You could print thousands of parts in one printer. Next is speed. So all of our printers are based on binder jetting technology. This is, it uses a printhead. And the printhead has a whole array of nozzles in it. And the printhead sweeps across the print bed, and as it does, it selectively doses binder. So instead of some of these printers that have a highly focused pinpoint that melts or sinters the material together and slowly scans across the surface, we can sweep across twice, and we do the entire bed area. So you can see that's going to be somewhat faster than a little laser that goes across the entire print area. Next, we've got cost efficiency. So you can use our systems, but you don't have to fully use 3D printer and additive manufacturing in your foundries. You can use it in conjunction with traditional tooling. You can hand ram some cores. You can blow some cores. You can make the cope and drag as you want. Just use us for the fragile pieces that you won't be able to do any other way. And that allows a synergy and cost efficiency. Next, we've got diversity in materials. So this is really in comparison to metal printing. So metal printing, you can only print in a handful of metals. Okay? Whereas us, if we work with a foundry, we can print or we can produce any castable alloy. So you can see our product range, the end product range of the supply chain we're part of, is much, much more diverse. So this is actually meant to highlight metal printing now. Sorry, no, it's foundry applications. So I've categorised the foundry applications into 5 main categories. So you might want to print a part to take to a boardroom with you to show to a client so they can feel it, look at it, check the internal cavities, does it make sense, does it match with the ideas they have. Next, you've got printing a pattern for the investment casting industry. This could be a printed wax, it could be a printed SLA part, it could be one of our prints. Next, you've got a pattern for the sand casting industry. So this is using it to make an impression in your bed of sand to make a cope or a drag. Next, you've got printing direct in sand, as I've just gone through. Next, you've got direct metal printing. Foundries that I've been to so far don't operate metal printers, but in the future, who knows, it might happen. So the techniques and processes out there in 3D printing are huge, it's diverse. Where do you start? How do you understand all the different techniques and processes out there? So I've got this diagram here, and it kind of gives you an overview. I have to say it's a generalisation, so there will be exceptions to the rules, but it's a very good way to quickly understand all the processes out there. So to your far right-hand side, you have VAPS photopolymerization, and then to the far left, you have sheet lamination. So I'm just going to take you through these bit by bit. So sheet lamination to start off with. I start here because this was one of the very first commercially available technologies. It works with paper. So you take the paper, you put glue to it, you cut it, and you layer it up bit by bit. Unfortunately, there were a lot of fires in the early days. Cutting paper with a laser isn't very good. It causes a lot of fires. But now there's some really smart systems out there. MCore have produced a fully colour system. And there's also a composite system that works on this process as well. So that might be competition for people who make metal parts when it comes to lightweighting and looking at alternatives to metals. So these technologies are developing. The composite side of things, they're not great at undercuts at the moment. But as with all of these technologies, they're advancing. I've grouped these 4 together primarily because they have a lot to do with foundries. These 4 processes here all offer investment casting materials. So to your far right-hand side, you have VAP photopolymerization. You have an SLA print that can be used in the investment casting industry. Same with material extrusion. This is the sort of process that you see with the little tiny printers that go on desktops. And they've got that nozzle, and it extrudes a spool of plastic, and it deposits it on a platform, and then either the platform indexes, or the nozzle indexes, and it layers up the part, and the material you can use can burn out, so it can be used in the investment casting process. Material jetting, this is what wax prints use. It uses this technology. And then finally, binder jetting. So this is voxeljet's bread and butter. This is what we do. They, generally speaking, are faster processes than the direct metal printing that use the laser that scans across the bed. Binder jetting, like I said, can sweep across whole areas rather than just points. The same said with that photopolymerization and material jetting. So next we move on to the processes that are mostly used in metal printing. So like I said, these are very slow. They're typically based either on laser or electron beam. They do have their applications, and I'm going to go through some of those very shortly. But when it comes to comparing them to our printing process, they're very slow. So, what's the point in using these things? I see three main points to it. So first, generally speaking, we offer some sort of speed advantage. Next, cost. And thirdly, complexity. So there's people out there that you say you get complexity for free with 3D printing. That's not strictly true, okay? Because when you print the part, you then have to unpack it and clean it. So there is time spent cleaning these parts, and the more complex it is, the harder it is to clean. The things that we print at voxeljet are single-use tools. So when you print a pattern for investment casting, when you print a mould for sand casting, you pour the metal in, you can only use it once. And obviously, if you want to make a number of units, eventually there's going to be a point where it makes sense to tool, because a tool can produce hundreds and thousands and tens of thousands of units. So if you can see this graph here, this is what it represents. There's going to be a point where if you want to make multiple units, a tool is going to be printing. But for those small quantities, printing can be very, very good. Next, metal printing. So, take a look at these 5 parts here. These are the poster boys of metal 3D printing. These are the ones being banded around on LinkedIn and Facebook profiles and Instagram saying, look at us, look what we can do. They're very complex. But actually, if you look at the geometries of them, I think the tooling would be hard to create, but perhaps if you used additive manufacturing for some of the cores perhaps, or a pattern for investment casting, I think you can make the metal flow from one part to another. I think they're castable. You don't have to print these out of metal. So these are some of the headline things in the news when it comes to technology and 3D printing. So as you're all aware, I suspect, GE have purchased 2 of the biggest metal printing companies out there, both Arcam and Concept Laser, for just over $1 billion US. They predict fantastic things for this technology. They expect to achieve revenues of $1 billion US by 2020. They expect to print 10,000 metal parts in the next 10 years, and they expect to sell 10,000 metal printers in the next 10 years, and they expect to print 100,000 metal parts by 2020. And then we've got 2 commentators in the industry here, Free Diligent and Smartech. So Free Diligent are saying it's going to change the aviation industry. That's all to do with a very fashionable lightweighting hype you see at the moment. Trying to make parts lighter, but provide the same functional properties. And then Smartech, they predict that 3D printing, 3D metal printing that is, will have a value of $6.6 billion US in 2026. To give you some sort of kind of scale of where that is in terms of castings, I've got the German casting market figure down here, and at the moment that's around $16 billion US. So you're talking 40% of the German casting market in metal printing by 2026. So you can see it's not going to take over the world. It's going to be used for niche applications, things that are very, very complex. And even then, you don't necessarily have to use this. You can still cast. So, this is a bit of a commercial study that was done in the US to find out how expensive metal 3D printing is. We surveyed the 3 biggest printing companies in the USA. We asked them to print in stainless steel 17.4, and we asked them about these 5 parts here on the right-hand side. So number 1 is a very simple part, and then as you go down, it becomes more and more complex. So if you have a look at the graph, the first thing to notice is part number 5 is a lot more expensive. And that's because it's very complex. But actually, if complexity was free, which a lot of people were saying on 3D printers, why would it be up there and the other 4 down here? It's because complexity isn't free. Once this is taken out of the printer, we have to have an operator use a paintbrush or a compressed air to clean that part with all of its complex little cavities. The next point to notice is, if you look at the 4 more simple parts, if you like, they taper off gradually with number of units, but it's not a large tapering off. You don't see scales of economy on metal 3D printers. It's because they're small and they're slow. So if you want to produce in mass, you have to have whole halls of these things. You don't get scales of economy with metal 3D printers, not at the moment. So to give you some sort of indication of how expensive they are, the average price was $12 US per cubic centimetre, which equates to a massive £1,130 per kilogram. We've got figures in casting of about £5.60 pounds sterling per kilogram to £28 per kilogram, depending on the sort of application. However, they will get better. So people are predicting they will increase their output by 25 to 45% by 2020. Some of the entry-level models will be reduced in price by 60%. The metal powder prices will reduce. And due to kind of the light-weighting movement in the industry and people to kind of topology optimize a lot of parts, it will play into the hands of these printers. People are saying it will change the aeronautical industry, improving parts by reducing their weight, keeping the same strength, or improving their strength and keeping the same weight. It's still not going to beat casting. It's still way off. So, OEMs are looking at metal 3D printers, and we're doing everything we can to tell them that actually metal 3D printing isn't the only way forward. Castings are there. Castings can perform better, they're cheaper, and you can achieve the same complexity. So, this part here is a great example. This was cast. This is an investment casting. It's part of a seat frame for an aeroplane. Autodesk did a case study. They metal 3D printed one and they cast one. The casting was 30% cheaper, and you could do it in a single part. If you metal 3D printed that, you have to do it in 4 parts. And how on earth do you assemble 4 separate pieces of this and try to connect the intricate lattice structure? It's just not doable. So a little bit about developments in sand printing and the printing out there for investment casting. So like our metal competitors, we're also improving. We're also developing what we do. So to start off with, we see ourselves getting faster. At the moment, we print at about 127 litres per hour on our sand printer. We expect to see that improve by about a factor of 3 to 400 litres per hour. So our mid-range printer, the 1 metre by 500 by 600 space that I was talking about, that could print in 45 minutes if we see that improvement to 400 litres per hour. It's all, because we're a German company and we've got close links to the automotive industry, this sort of strategy is aligned with them, but ultimately it can be applicable to all industries and everyone's going to see the benefits. Next. You're going to see new materials. So the inorganic binder system is in development, and we hope to see that coming to fruition in the coming years. When it does, it'll be very good, there will be no harmful emissions, we can deal with our waste a lot better. And then finally, automated post-processing. So at the moment, the post-processing, as I've alluded to, can be quite labour-intensive. You know, you buy a printer thinking, it's all going to be done in some fancy machine. Hey presto, your part pops out, very complex, but actually the reality is once it pops out, you then have to clean it. So getting things like KUKA robots downstream of the printer that are firstly removing the unprinted loose sand and then cleaning them up is going to be a massive step, and we hope to achieve that. On the softer side of things, I think the printing industry out there can improve on their support, so educating people how to use their printing systems, people who operate the machines, giving them service support, giving them training on how best to operate them. I see software being developed out there that allow you to design components for additive manufacturing, and all of these things are having a synergy and seeing this industry really take off. And then finally, I'd just like to leave you with some parts that we've printed and the cast parts that they've created. And then that's it, thank you.
Thank you, Gareth, for that very informative overview of 3D in action as it is now. I'm just wondering if anybody has any questions for Gareth. Please?
Yeah, in terms of your 3D printed SAM, they all say that the structures are not as strong as a round core, for example, or a round mould. By how much less is the strength of the 3D printing compared to a conventionally made core or mould?
Sure. So a hand-rammed core, depending on how well the person rams it into the mould, I suppose you're going to get big variance in those strengths that you see. What I don't have a direct answer, unfortunately. But what I can tell you is, when we deliver these printed parts, we typically have no problem whatsoever. Yeah.
Yes.
So we're using some pre-printed moulds in our foundry. We're a jobbing outfit, I suppose, or semi. What's the alternative binders systems? If we put a mould into you or a request into you, can you do alkaline phenolic? Because the ones we use at the moment are not.
We can do phenolic, yeah, so there's not as much printing capacity out there for phenolic, but we do have phenolic capability, and we'll be happy to work on that with you.
Any more questions anywhere? Well, thank you. If you'd like to join me in thanking Gareth for his presentation today.